Okay, so the problem seemed to be fixed now. So we are in section 4.4 now. I'm sorry, 4.5. We did 4.4, and this one is dealing with rational functions. Okay, so a definition is pretty straightforward. The definition of a rational function is a function of this form, f of x equals p of x over q of x. So it's a fraction where both p and q are polynomials. So you have a polynomial divided by a polynomial. And the domain of this function will be every time this kind of the same way. We're going to find in the domain. It's just all x's such that the denominator is not equal to 0. So just make sure denominator is not 0. And we've dealt with domains of rational expressions before. Just whatever makes your denominator equal 0 has to be excluded from the domain. Okay? Regardless of whether you can simplify it or not. That's the big thing here. It's whatever turns your denominator into 0 before you even simplify that. So a few examples, just finding the domain. And we've done that before, but now we're just looking at it in a more functional notation. So let's say f of x equals something like this, x minus 3 over x squared plus x minus 2. So all we really have to do is to find zeros of the denominator. And the easiest way to do that is to factor first, and then we understand how the factors and the zeros play together. So we can factor the denominator into, oh yeah, x minus 3. So x plus 2, x minus 1. Is that correct? So what are the zeros of the denominator? Negative 2 and 1. So these are the numbers that are not in the domain. So the domain of this function would be all real numbers such that x does not equal to negative 2 and x is not equal to positive 1. Okay? Regardless of whether we can reduce this fraction or not. Okay? Here's another example. Let's say I have something like this, x cubed over x cubed minus 9x. So that's another example of a rational function. So we need to find the zeros of the denominator. So we're going to do some factoring. So x cubed goes in the numerator, then we can factor out x squared minus 9, and x squared minus 9 is the difference of two squares. We can factor that into x minus 3, x plus 3. Okay? So what are the zeros of the denominator? 0, 3, and negative 3. So these are the numbers that are not in the domain of this function. So all x is such that x is not equal to plus or minus 3, x is not equal to 0. Okay? Although I can simplify this function, I can cancel x, right? I can reduce it by one of the x's to get down to x squared over x minus 3, x plus 3, but that will not affect my domain. 0 still has to be excluded. So it has to be judged by the way the function is written originally. So now we kind of talked about that. What that does to a graph of a function just creates a hole in the graph. You're going to have nice pretty lines going, you know, almost meeting, but there's going to be a hole where x equals 0. Okay? So it's going to look something like that at 0, maybe. So kind of like that. Just going to have a one hole in the graph. Okay. Because eventually we're going to try to graph a function like that. We're going to try to graph things like that and see what the graphs look like. And it's not that bad. Okay? So let me take this function again. F of x equals x minus 3 over x plus 2x minus 1. So we already said the domain of that function is all real numbers except for negative 2 and positive 1. So that means this function is defined for all other values of x, right? No matter what x is, I can plug it in, and I'll get a nice answer, which is a real number. The only two numbers that I cannot plug in would be positive 1 and negative 2. But the question is, well, what will happen when my values of x are really, really close to negative 2 and really, really close to positive 1? Because technically, I can go and plug in x equals 0.9999. I'll get a real answer out of it. Okay, so let's kind of talk about this. So the question is, what happens when x is really close to negative 2 or positive 1? Okay? So for example, so I want to just compare x with f of x, and I'm going to take numbers that are close to 1. Can you give me some examples of numbers that are close to 1? Okay, 0.9, right? 0.99, somebody said 1.1, right? I can be close to 1 on either side, right? So let's say 1.01, 1.1, right? So that's going to be really, it's going to be a little pain in the, you know, whatever you want to experience pain in to compute this, because I have to literally plug in 0.9 in for x, and it's just ugly, right? I mean, I'll do it once, and then we're just gonna apply some kind of analysis to that, just kind of talk out loud of what's going on. So if I plug in 0.9 in for x, can we do that computation in our head? So if I plug in 0.9 in here, I'll get 2.9, right? If I plug in 0.9 in there, I'll get negative 0.1, right? And if I plug in 0.9 in there, I'll get negative 2.1, right? So if I compute that, so see what happens. It is 2.1 negative divided by a product, I'll put in the parentheses, of 2.9 times 0.1 negative. So just some weird number, positive 7.2, who cares, right? But positive number. You agree with that? So we got something like 7.2-ish. But if I get closer, if I do 0.99, so how will that change? My 2.9 will become 2.99. Negative 0.1 will become negative 0.01, right? And the other thing, if x is 0.99, I'll get 2.01. And if I plug that in, see what happens. So 2.01 negative divided by the product of 2.99 times 0.01 negative. So I got 67, right? So the number just kind of jumped really drastically, right? So 67-ish. And if I get even closer, if I'll try 0.9999, let's say, just for fun, I'll put 0.9999 in there. What do you think will happen? It will be even bigger. And the reason for that, because the closer you get to 1, the closer one of your factors gets to 0, right? So if one of the factors is 0, that means the denominator is very close to 0. And if you're dividing by numbers that close to 0, you're going to get really, really big results, right? If I do 0.999, I'll get 2.0001 negative divided by the product of 2.9999 times 0.0001 negative, bam, there's going to be some, ridiculous number, okay? So the closer we get to 1, the bigger the numbers get, right? But at the same time, if I plug numbers like 1.001, if I change that, what will happen? Now my numerator, if it's 1.001, my numerator will be negative 1.999. This will be, right here I'll get 3.001, and over there I'll get 0.001. Right? I'll still get a very large number, but the difference will be that that number will have a negative sign. So we're getting large negative numbers, okay? So what it looks like, if I look at the graph, if I think about the graph of this function, that when x equals 1, and as I'm getting closer and closer to 1 from the left side, so 0.9, 0.99, 0.999, the values of my function appeared to shoot really, really high. They were very large positive numbers. And at the same time, as I was getting closer to 1 from the right side, 1.1, 1.01, so forth, we're getting a really large negative number. So we're jumping down there. So it looks like the graph of this function does something like that, around x equals 1. But it never gets to x equals 1. I cannot plug in x equals 1. It's kind of an invisible barrier that goes through x equals 1. We cannot touch that. But generally the graph looks like that. Are you okay with that? Yeah? Okay. Now, we will, again, you might have noticed I'm really anti-table type of guy. I don't like doing that, plugging numbers in. So we can kind of predict the result. We know that things will get really large or really small, okay? So the only question is, what is the sign, whether it goes up or down? So you can kind of guess. If you take value for x that's less than 1 and you plug in for x, the numerator will be negative, right? If it's slightly less than 1, the numerator will still be negative, x, right? Something less than 1 minus 3 is always going to be negative. While in the denominator, something positive plus 2 is positive, and then something less than 1 minus 1, that's negative. Do you agree with that? So it's a minus divided by plus times a minus. Overall, it's a plus. So it's going to go up. On the other side, the parenthesis x minus 1 will produce a positive result because you're staying slightly above 1. So slightly above 1 minus 1 is positive. So you're going to have a minus in the numerator and then 2 pluses in the denominator. So it's a negative. Yeah, I'll repeat that 17 more times throughout, so don't worry about it. Now we have a special name for those kind of invisible barriers. We call them asymptotes. The graph of the function gets really, really close to those asymptotes, but doesn't quite touch them. And we'll have three types of asymptotes. This is the first type called vertical asymptote, because it's, well, vertical. And to find them is really simple. It's almost equivalent to finding the domain. Okay? But do you understand what I mean by an asymptote? That's kind of a barrier that your graph gets really, really close to, but doesn't quite touch it. I mean, just doesn't touch it, period. Okay? All right. So we're talking about asymptotes now. So the first type of asymptote we're going to talk about is the vertical asymptote. Okay? So it's almost equivalent to finding the domain. The difference between finding, and this is the important distinguish between domain and the vertical asymptote. With a domain, we'll look at the function as it's written before we even simplify it. Whatever makes denominator equal 0 is excluded from the domain. While the vertical asymptote is the same thing, only after you reduce the function. Okay? So you reduce first, and then you look what turns the denominator into 0. Okay? So to find the vertical asymptotes is to look at f of x equals p of x over q of x in the reduced form. Meaning p and q don't have any common factors. So then the zeros of the denominator are the vertical asymptotes. So our function, the one we just looked at, x minus 3 over x plus 2, x minus 1, has two vertical asymptotes, at positive 1 and at negative 2. So it will have those kind of invisible lines that your graph will try to avoid the best that it can. Okay? So that's how you find vertical asymptotes. It's actually really simple. It's almost the same as finding the domain after you reduce the function. So if I go back to my early examples, when I look at the second one, right, the domain was all real numbers except for plus, minus 3, and 0. But what are the vertical asymptotes? Well, 0 is no longer vertical asymptote because we're looking at our function after we reduce it. Okay, so to find the vertical asymptotes, you reduce first, and then look what turns the denominator into 0. Because again, 0 will just make a hole in the graph. It won't make that type of thing. Okay? So reduce first, and then look at what turns the denominator into 0. So in this case, the vertical asymptotes are plus or minus 3. So when we looked at this function, x cubed over x cubed minus 9x, we were able to reduce it to this. So the vertical asymptotes are only positive or negative 3. 0 is still not in the domain of this function, but it's not a vertical asymptote. Okay? All right. So any questions on how to find vertical axis? So whatever turns the denominator into 0 after you reduce your function. Now, the other thing that we want to talk about, what happens to our function as x gets really, really big or really, really small? Okay? So also want to discuss the values of the function. On extreme values of x. Really big or really small. Meaning really big as x gets closer to infinity, or really small when x gets closer to negative infinity. What's happening to the shape of our graph? Because there are a few things that can happen as x gets big, and that will help us to determine what the graph is going to look like. So if I go back to this function right there, okay? So let's pretend we're going to be substituting large values of x in it. Just give me a large value for x. 100, okay? Now check it out. If I plug 100 in for x, I won't be writing anything down. What is the numerator? Still around 100, right? I don't need it exact. It's 100 minus 3, so it's around 100. While denominator, it's something close to 100 times something close to 100. So that's close to 10,000, right? So because it's a linear, if I go back to the way this function was written, it's linear over quadratic. So when I plug in 100 for x, I'll get something close to 100 divided by something close to 10,000. Is that number small or big? Small, right? It's 100 divided by 10,000, so it's kind of a 1 over 100, so it's 0.01. If you go higher, if you plug in 1,000, your numerator will still be close to 1,000, while your denominator will be close to 1,000,000. 1,000 over 1,000,000 is even smaller, right? So the larger x gets, the closer you get to 0. Do you agree with that? If you plug in really large values for x, this ratio right here will get closer and closer and closer to 0. You plug in 1,000,000 for x, you'll get 1,000,000 divided by, what is 12 zeros? A trillion? Right? So that's small. Okay, so it seems like as x goes to infinity, the value of the function gets closer and closer to 0, but doesn't quite get there. So the graph will be doing something like that. It will be flattening out as x goes out to larger values. The graph will be getting really, really close to the x-axis. That's where the function is 0. Either from below or from above. I don't know exactly how. We'll figure that later. But at least we know it's going to be getting closer and closer to the x-axis. At the same time, as x goes to negative infinity, so as x gets really, really small. So if I plug in negative 100 in for x, I'll still get something close to 100 over something close to 10,000 and so forth. I'll still get closer and closer to 0. So on both ends, the value of the function gets closer and closer to 0. Are you okay with that? All right. So, but that's what we're trying to do, and that will give us what we call a horizontal asymptote, is when the graph kind of evens out. Okay, and I'll teach you how to find a horizontal asymptote, so we don't have to plug in numbers and things like that. So, horizontal asymptotes. First of all, let's take this as a rule. If you have, consider this expression, any constant divided by x to any power, like that. So r is positive, a is just a real number. Then this thing will go to 0 as x goes to infinity or x goes to negative infinity. Well, that means your numerator stays fixed. It's a constant. Your denominator gets bigger and bigger and bigger and bigger and bigger. So the ratio of constant over bigger is always going to be small, close to 0. Are we okay with that? If you keep dividing a number by bigger and bigger and bigger numbers, you're going to get very, very small results, closer and closer to 0. Do you agree with that? Say yes. Yes, good. All right. So now again, to find horizontal asymptotes, I'll be abbreviating it like that, HA, horizontal asymptote, we need to study what happens to the values of our function as x gets further from 0. So meaning infinity or negative infinity.
So with the other ones, the x equal, would that be 1?
But maybe. No, that was, I think I had to say as, no, as x. Yeah, I wanted to say as x, I wrote ax. As x gets further from 0. So let me give you 3 different cases. Let's say we have this problem. Let's just go back to our first question. X minus 3 over x squared plus x minus 2. Again, we want to know what happens to this function as x gets really big or really small. That's the job here, to find the horizontal asymptote. So one way to do that is to look at the degree of your denominator. What is the degree of your denominator? 2. So if the degree of the denominator is 2, I'm going to do the following. I'll multiply both numerator and denominator by 1 over x squared. Is that a legal move? I'll multiply by 1, so that's legal, right? And I made my 1 to correspond to the degree of the denominator. Okay? Well, I use the same power, basically. So I'm doing 1 over x to whatever degree in the denominator is. Now, see what happens. As I multiply 1 over x squared by x, what is 1 over x squared times x equals to? Well, it's 1 over x, right? This product is 1 over x. The next product is 3 over x squared, right? Just distribute. How about here? What is 1 over x times x squared? 1. Now 1 over x squared times x. What is that? 1 over x. And negative 2 times 1 over x squared? Negative 2 over x squared. It's the same problem. What? Well, I haven't finished it yet. You'll see why in a second. But now let me ask you this. As x gets really, really big, what will happen to 1 over x? What 1 over x gets close to as x gets big? 0, right? Based on what I wrote here. Every time you have a constant over x to some power, it's going to go to 0 as x gets big. So this expression goes to 0. How about this expression, 3 over x squared? Where is that going to get close to? What? 0. How about this guy? 2 over x squared. 0. How about this guy? 0. How about this guy? Yeah, so just 1, right? So this whole thing looks like 0 over 1 as x gets big. And what is 0 over 1? 0. Okay? So that's kind of an algebraic way to show that everything will collapse to 0 if x gets really, really big, without plugging in numbers. Well, then I'll have to make a lot of logical jumps, and that's not good. Because what if you miss? That's okay. I didn't do anything spectacularly weird. I just multiplied by 1, used the distributive property, right? Let's try another one. How about this? G of x equals 3x cubed minus 4x divided by x squared minus 5. Yeah. Yeah, so the horizontal asymptote is 0, so it's just the horizontally, so it's just the x-axis. Okay. Now, how about this one? We're going to start the same way. We're going to look at the denominator and identify the degree of the denominator, which is what? 2. So then I'll do actually the identical. I'll go, all right, 1 over x squared over 1 over x squared. Okay? So if we do that same distribution, what is x cubed times 1 over x squared? 3x, so we get 3x. How about 4x times 1 over x squared? So 4 over x, right? We're still going to end up with 1x in the denominator. How about here? We'll just get 1. I don't like that question because I'm going to give you the answer that you don't like. Yes. So just sit tight. But we don't. See, that's the thing. I'm not saying that it's going to be 0 because look, what happens to 5 over x squared as x gets big? Where's that going to go? No, 0. Every time you have x in the denominator and x gets bigger, 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 the ratio will get closer to 0. How about 4 over x? Where's that going to go? 0. 1 equals 1, right? 1 is not going to go anywhere. But this is 3 times x. So as x gets big, what is 3 times x going to get? Big, right? So 3x will actually go to infinity, depending on, the values of x. As x gets big, 3x gets big. So you're really ending up with something big over 1, right? Which is big. Now, is big a number? What?
Infinity.
Right, but so is infinity a number then? No. So then there is no horizontal asymptote. The function is not evening out, it's getting bigger and bigger. What's with the attitude? Yeah. Well, either way, as x goes to infinity, it will go to infinity. As x goes to negative infinity, it will go to negative infinity. So it flies out. It's not going to even out around some number. It's just going to go high and low. So no horizontal asymptote. So, because again, for the horizontal asymptote, we're looking.
Could you just say that it's
Oh, stop it. I'll get to that. Stop thinking ahead of me. Because I might say no. I'll make you do that every time. Is that what you want?
you said we do have to do this every time.
Yeah, I know. We might have to do this every time. But hang on there a second. I'm just going to stop right now, and I'll just let you figure this out on your own. One more case, okay? But again, we're just trying to see what happens to the values of our function as x gets further from the origin, so really large or really small, okay? So in the first case, it looked like no matter what x is, as long as it's getting big, we ended up with a 0. That means our function will be diving onto the x-axis and evening out there, flattening out at the x-axis. While in the next case, we got infinity, so the function will just fly out, doesn't approach anything. Question? Never mind. Not really. It really has to do a lot with exponents. That was the big thing here. What are the exponents? But if we try this example, let's say negative 2 x to the power 4 minus 3x plus 1 over 7x to the power 4 plus 2x squared minus 7. So just made one up. Okay? And again, we want to try to identify the horizontal asymptote of that function. And we'll start the same. We're going to look at the denominator, and we'll identify what is the degree of the denominator. 4. So we'll just go 1 over x to the 4th, 1 over x to the 4th. And we'll play the same game. We'll try to distribute. We do 1 over x to the 4th times the first term. What will that equal to? Negative 2? See, it's not that bad. How about the next product? What will that equal to? Negative 3 over x cubed. How about the third product? It's just 1 over x to the 4th, right? All over. What happens when we multiply by 7x to the 4th? 7, and then the next product. 2 over x squared, you said? And finally? Okay. Is that okay? So basically, I just rewrote my function in a kind of a weird way, but what happens to 7 over x to the 4th as x gets big? Where's that going to go? 0. How about 2 over x squared? 0. How about 1 over x to the 4th? 0. How about 3 over x cubed? 0. But negative 2 is not going anywhere. It's negative 2. And 7 is not going anywhere, right? Negative 2 is just a constant. Doesn't matter what happens to x, and 7 is just a constant. So it looks like this whole thing equals what? Negative 2 over 7. So negative 2 over 7 is our horizontal asymptote. The function will get closer and closer to the line y equals negative 2, 7. Okay, it will be flattening out at that height. So the horizontal asymptote negative 2 sevenths. So the function will get closer and closer to those values as x gets further from the origin. So it will be flattening out. Okay? Good. Now tell me, what do you want to say? What is the pattern here? I know you noticed the pattern a mile ago. What is the pattern? Can I predict what my asymptote is going to be without doing the division? Yes, how do you predict that? How do you know whether you're going to get 0 for the horizontal asymptote? Right. If the degree of the denominator is bigger, every time the whole thing is going to collapse to 0. Okay, so we don't have to do that anymore. How about when do we get no asymptote? What has to happen? Bigger on top. If the numerator is bigger, then it will eat out the denominator, so it's going to go to infinity. So 0, if the degree of the denominator is bigger. Infinity, if the degree of the numerator is bigger. What about the last case? So if the degrees are the same, then what do you end up with? Yeah, so the ratio of leading coefficients. All right? Yeah, I'm going to make it in a more prettier. Yeah, well, not a theory, more of a guideline. So, but this is kind of why, because it's kind of a proof why that happens. So you don't have to do that unless you like that. And there'll be a class where we'll make you do that. You won't be able to just say, well, based on what I learned in college algebra, the asymptote is 5. And you're like, well, yeah, in another class. But so now, finding horizontal asymptotes. So let your function be this. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way, polynomial, right? In the numerator. In the denominator, you're going to have a different polynomial, so let's call it b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus all the way to b sub 1 x plus b sub 0. So you have two polynomials. Numerator has a degree n, denominator has a degree m, right? So now, if m is greater than n, meaning degree of the denominator is bigger than degree of the numerator, what did we agree horizontal asymptote is going to be? If the denominator is bigger than the numerator, 0. Then horizontal asymptote is y equals 0. Okay? Is that nice? 2, if the degree of the numerator is bigger than the degree of the denominator. So numerator is growing faster, it's a much larger polynomial, then what is the horizontal asymptote? None. Then no horizontal asymptote.
So it can only have one horizontal.
Well, you can have, yeah, you can only have one. For rational functions. You can have other functions that might have different horizontal asymptotes. And 3, finally, if the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is the ratio of leading coefficients. So in this case, horizontal asymptote is y equals a sub n over b sub n. So ratio of leading coefficients. How is that? Super. Now, a big important note. As we're about to start graphing these things, so we cannot cross the vertical asymptote no matter how tempting it is. So we cannot cross. No, there's going to be a third type as well. But for now, let's focus on this too. There's also going to be a slant asymptote or oblique asymptote. But you can either have horizontal or oblique. You cannot have both. But anyway, so we cannot cross vertical asymptotes. No matter how hard you try, don't do that. Because that means you dividing by 0, you're crossing things that are not in the domain. Now, horizontal asymptotes, it is okay to cross those for small values of x. Okay? Sometimes you just kind of have to. So that's all right. Nothing bad happens. It is okay to cross horizontal asymptotes for smaller values of x. So it's, again, horizontal asymptote only matters in the long run. What happens with the large values? But for small, sometimes you just have to cross it. Nothing bad happens. Horizontal asymptote, it only tells us what happens when x is large. Well, just hypothetically speaking, let's say if you have a graph, don't write this down, but let's say you have a horizontal asymptote like this and like a vertical asymptote like those two. And your graph might look something like that, but in the middle it can do this. So here we go, we just cross the horizontal asymptote, and that's okay. Nothing bad happens there. But in the long run, your graph gets closer and closer to those horizontal asymptotes. That's what matters, really. That's what horizontal asymptote tells us. What happens to the graph as x gets large. Okay? There are functions, not necessarily rational functions, that can do, if this is a horizontal asymptote, the function can do this to it, kind of crosses it infinitely many times, but the amplitude of the crossing gets smaller and smaller and smaller, so eventually it evens out and approaches that asymptote. But so it's okay to cross horizontal, nothing bad happens. Vertical, out of, cannot touch those. Okay? What? Fun stuff? I'm picking up so much sarcasm that it hurts. All right. Now, all those asymptotes, we need them to graph those types of functions, because most of your calculators will explode if you try to graph a rational function, because they don't understand asymptotes. It will start dividing by zeros. It will give you a bunch of lines. So I'm not even going to test that, but it's simple to do it. All right. Let's try this example. Very friendly. X squared minus 4 over x cubed minus x. No, I don't like that one. Let's try x squared minus 1. A little simpler. Here we go. All right. So it's always helpful to, I want to sketch the whole graph of that thing. See what's going to happen. I'll lay out all the steps. Okay. So first thing you should always do is to factor everything that you can possibly factor. So when we graph these types of functions, the first thing you should find would be your x and y intercepts. Okay? So the first thing to find is to find x and y intercepts. So remember, in order to find the x-intercept, we'll set y equal to 0 and solve for x, right? That's the general concept of finding the x-intercept. Now, for this particular case, a fraction can only equal 0 when numerator equals 0. Right? You agree with that? Because denominator cannot equal 0, period. So we want our numerator to be 0. Then the whole thing equals 0. So really, in order to find the y-intercepts, to find the x-intercepts, you just have to find the zeros of your numerator. So whatever makes numerator equal 0, which is what? In this case? 2 and negative 2. So those are your two x-intercepts. Okay? So for rational functions, all we have to do is to find zeros of the numerator. So in this case, it is, So if the numerator equals 0, then the whole fraction equals 0. So I can actually start somewhere down on the page doing a little sketch. I can start doing the sketch because right now I know this. Negative 2, we're going to cross that. Positive 2, we're going to cross that. So we have those two x-intercepts already. So we know that much. Is that okay? Y-intercepts? Well, that's the same. To find the y-intercept, we're going to set x equal to 0. So set x equals to 0 and solve for y, so in this problem, if you set x equal to 0, you'll just be left with this ratio, right? -4 divided by -1, so 4, right? So in our case, we'll get y equals -4 over -1, so 4. Y equals 4 is the y-intercept, so I can actually label it on my graph. You know, whatever. This is, let's say that's 4. Good? Good. Now, so that was the first thing. Find the intercepts. Second step, find the vertical asymptotes. If any. Because, you know, you might not have any vertical asymptotes, which is, bless you, totally okay. Now, vertical asymptotes, they're real numbers. Just making sure. So, for this function, when your denominator is x minus 1, x plus 1, what are the vertical asymptotes? 1 and -1. Whatever makes the denominator equal 0. So, zeros of the denominator are vertical asymptotes. Remember that. So in this case, x equals 1, x equals -1. All right, so here's 1, so we have a vertical asymptote here. And here's -1, we have a vertical asymptote there. It should be, you know, same distance from the origin. My graph is out of, know what I mean? Okay, it's a little bit out of, not drawn to scale. But we got those two asymptotes. Is that okay? Now, third step, find horizontal asymptote, if any. Well, when you look at our function, which had a quadratic divided by a quadratic, so it's the same degree, you're miming 1, and the just ratio of coefficients, which is 1 over 1. So 1, okay? So the vertical asymptote, y equals 1. So that was nice and friendly. So here we go. Right? This is what I have right now. So now if I ask you to actually do the sketch of this graph, that means, you know, you have to touch your intercepts, and you have to, what I like to call, respect the asymptote. So, you know, get close to them. Asymptotes are like black holes. They just suck the graph to them and gets closer and closer. So the fourth step, in this case, would be to sketch the graph and respect the asymptotes. Sometimes you have to find some extra points where it's not clear where the graph goes. Sometimes you just have to do that. Not in this case, because it should be pretty clear what we're doing, but sometimes you'll have to find, and we'll see example where we have to do the find extra points. But now let's talk about this graph. Think about this. So on this end, on the left side, we have the x-intercept, -2, so we have to hit that. We have to cross that point. But we also have to get close to the horizontal asymptote, and we have to cross, get close to the vertical asymptote. As closer we get, the closer the graph of the function gets. So there's only one way I can do that, right? How would you sketch the pro-sum limit, right? You have to get close to the horizontal, and you have to get close to vertical. So there's only one thing that you can do, right? There's no other option. How about all the way to the right? So same thing, right? It's kind of a So same thing. Do you agree with that? There's no other thing that I can do there. Now, for the middle. So look at the middle. There are really, right now, almost 4 options of what I can do in the middle. And I'm going to use the magic pen to draw 4 of them, and we'll realize only one makes sense. Because look, I just have to cross that point, right? I have to cross the y-intercept. I cannot touch the vertical asymptotes, but it is okay to cross the horizontal. So I can do something like that. Technically, I touched that point, and I didn't mess with the vertical asymptotes. It will disappear in a second. I can do something like that, right? And it will go away in a minute. I can do something like that, kind of a parabola-looking thingy. Again, stays within the asymptotes. And I can do the upside-down parabola like that, right? So out of those 4 options, only one is valid. Which one do you think? It goes like that, right? Why? Why is that the only option that's valid? Why is it the only parabola that goes up? No, it has nothing to do with that. Not necessarily. The asymptotes just need something to get close to them. Why is it a parabola that goes out like that? Goes up. And for those of you who are online, I'm standing with my arms raised to the skies right now, pretending that I'm a parabola. Why is it that one? Why it cannot go down? Why it cannot do the cubic thing? Well, if it did any one of those 3 options, it will cross the x-axis, but we don't have any x-intercepts there, right? We found all the x-intercepts. So if we go down at any point, we will create the x-intercept that's not there. So you always keep that in mind. So it has to be that. Otherwise, you'll hit the x-axis, and we know we already found all the x-intercepts. There are no extras. No, no. But what I can also know, what I can use, no, that x squared has nothing to do with, it could have gone the other way. It's random. But if I ask you, is this function odd or even? Remember those? You replace x with a negative x. Well, all the negative signs will go away. This is an even function, right? So it has to be symmetric around the y-axis. Yeah, it's always helpful, right? So it's if I knew beforehand that it's an even function, so it's symmetric with respect to the y-axis, then it also helps to realize that it has to be, well, symmetric around the y-axis because it's an even function. So that thing comes up. It's always helpful to identify the symmetry before you sketch, because then a lot of questions will just be solved a lot easier. We would know that it has to be a parabola to stay symmetric, but then it cannot go down because of the no x-intercepts there. So anyways, that's it. That's the graph of that function. It's actually not that hard. I spent all this time explaining the horizontal asymptotes, but you know, you do the x-y intercepts, you do the vertical, you do the horizontal. If there are no horizontal asymptotes, we haven't talked about the 3rd type of asymptote yet, but how is that for now? Is that good? All right, let's try another example. F of x equals x minus 2 over x cubed minus 9x. No, we had something, maybe, I don't know. It's very close to the something we already did. No, we had an extra, no, it looks almost the same, but it's not. So anyways, So the first thing, try to factor everything. So if I factor the denominator, I should get x minus 3, x plus 3. Right? Nothing reduces. So first, find the xy intercepts. So the x-intercept, again, we just have to think about zeros of the numerator. So what are the zeros of the numerator? What? Right. So the only x-intercept is x equals 2. That's the only time where the function equals 0. Now the y-intercepts, we're going to set x equals to 0, right? Well, if I do that, what will happen? I'll get negative 2 in the numerator, but 0 in the denominator. So there's no y-intercept, right? So undefined. So no y-intercept. So the graph does not touch the y-axis. Actually, y-axis would be one of the vertical asymptotes. So we cannot touch the y-axis in this case. But so far, if I start my sketch, the only thing that I have is x equals 2 as an x-intercept. That's all that I have so far. I don't have any y-intercepts. I don't have anything else. Okay? So how about vertical asymptotes? So whatever makes your denominator equal 0 when it's in the reduced form, it's in the reduced form because nothing cancels. So what makes denominator equal 0? So x equals 0, x equals 3, x equals negative 3. So we have 3 vertical asymptotes. One goes through 3. One goes through negative 3. And the actual y-axis, the y-axis is also vertical asymptote. And this is one of the reasons why we don't have y-intercept. You cannot intersect the asymptote. Is that okay? All right. So let's see. And the horizontal asymptote, the degree of the numerator is 1. The degree of the denominator is 3. So degree of the numerator is smaller, so then it's 0. Okay? So since the degree of the numerator is smaller than denominator, the horizontal asymptote is just y equals 0. So the x-axis would be the horizontal asymptote. Good? Well, now, this is hard, because there are options. Because when your x-axis becomes your, where's my magic pen? Horizontal asymptote, on the left, I can either do this, right? That respects the asymptotes. It looks good. Or I can do that. Nothing prevents me from doing either one, right? And I really don't know which way to go. So this is where you can start plugging in extra points. Because if I take any number on the left side, any number that on this interval right here, let's say negative 5, for example, and I plug it into my function, I'll get a positive answer. That means the graph will go up like that. But if I take a number, plug it into my function, I'll get a negative answer, then the graph will have to go down like that. So this is where those extra points come into play, because I really don't know which way to go. There's no way for me to find that out. So at this point, we're going to start finding extra points. And again, all I need is the sign. All I need is a positive or is it negative. That's all I really care. So let's grab a number to the left of -3. Just whatever you like. Pick a number to the left of -3. -4. So f of -4. And our function will be -4 minus 2 over -4 times -4 minus 3, -4 plus 3. Right? It's always easier to plug into your function when it's factored. And you don't need a calculator here because nobody cares what it equals to. You just need a sign. Because look, let's talk about just the sign. What will be the sign of that numerator, -4 minus 2? I just need a sign of it. Is it positive or negative? Right? -4 minus 2. So that's a negative. And then I look at the denominator. It's a product of three things. First thing is -4. Is -4 positive or negative? Negative. Times -4 minus 3. Is that positive or negative? Negative. And how about -4 plus 3? Is that positive or negative? Negative. So what is a negative divided by 3 negatives? Well, because when we factor that, it had that x in front. So yeah, the whole thing will come out to be positive. But I'm using the factored form. It's easier. So it's positive, right? So it's above the x-axis, so it has to do this. So I need it. Is it positive? So then it's above the x-axis. Yeah, because I took -4, so to the left of that asymptote. Because again, if it stays positive above, I mean, it will stay. The whole thing will stay above because it does not have an x-intercept there. It cannot go down anymore. So that's why. Do you understand why we have to test that? Because if we have a point above the x-axis, the whole thing will stay above the x-axis because it doesn't have an x-intercept there. Okay? Got it? All right, well, let's keep going. What will happen between -3 and -3 and 0? Yeah, you can plug in a number again. So pick a number between -3 and 0. -1. So let's do the same thing with -1. So that will be -1 minus 2 over -1 times -1 minus 3, -1 plus 3. Well, but this one is positive, right? It's a minus over minus times a minus times a plus. -1 plus 3 is positive, right? So overall, it will come out negative, right? So that means it does that here, right? But yeah, it'll just be some kind of a negative parabola because again, in order for it to go up, it has to cross the x-axis, but it can't because there's no x-intercept, right? Is that okay? And now again, between 0 and 3, don't pick 2 because 2 will give you 0. But let's pick 1. What happens if I plug in 1 for x? And it will give me a point probably above the x-axis. F of 1 is 1 minus 2 over 1 times 1 minus 3 times 1 plus 3. So that looks like a minus over plus times a minus times a plus. Overall, that's a plus. Right? You can do that. This is perfectly acceptable. Because again, the question is it positive or is it negative? You don't care what it is precisely. So that means at 1 it's something positive, so it has to do that. but it has to hit that point, right? So it can do two things. It can bounce off 2 and go up again, or it can go down. Well, not necessarily, because I have the x-intercept. Okay, so I actually have to figure out what happens between 2 and 3 as well. Okay? Well, it can just touch, right? What I'm trying to say, I mean, you have to look at all options. It can do that, right? Or it can go down. What does your gut tell you will happen? It will go down, right? And your gut is exactly right. But you don't trust your gut every time. So we really have to test between 2 and 3, so like 2.5. So I have to really compute f of 2.5. So that's 2.5 minus 2 over 2.5 times 2.5 minus 3, 2.5 plus 3. So all of those are positive except for one. It's plus over plus times a minus times a plus. So it's a minus, right? So yes, it goes down. So it turns and goes down. So that's what I was saying. It is okay to cross a horizontal asymptote for smaller values of x. Okay? The horizontal asymptote really kicks in in the long run. But it is okay to cross it in the middle. The vertical ones you can never touch because that's division by 0. But horizontal ones, if you must cross it, well, we just did. You just have to in this case. And the last thing, I need to figure out what happens when x is greater than 3. What does your gut tell you will happen? Is it going to be positive or negative? What? Negative, negative, positive, 2 against 1. Who else is going to vote? 2 negatives, 1 positive. Anyone? Okay, 3. All right, 3, 3. We need a tiebreaker. We have. I know. I don't need a gut to tell me. I know what's going to happen. But okay, pick a number greater than 3. How about 24? Right? If I take 24 and I plug in for every x, all of those factors will be positive, right? 24 minus 2 is positive. 24 minus 3 is positive. So all of them are positive. So what is going to be? Positive. So the whole thing will stay above the x-axis like that. What? Wasn't that fun? Now let me teach you something that will save you a whole lot of time. Well, you have to understand the mechanics, and then I can give you the short. That's the whole idea behind math. We can all start with every problem can start with the concept that 1 plus 1 equals 2, and then you build on that. That's really what happened. Now, here, all I need to do the graph of this function is just one of those points. All I need is just one. I don't need, how many did I do? 1, 2, 3, 4, and then we did 5 verbally with 24. We didn't write that down, right? We did 5 computations. All I need is one. Because I know one thing. Well, there are a few things, but do you remember we talked about multiplicities and all that? When we talked about polynomials, how with the multiplicities, if multiplicity is even, then the function bounces off. That means the function doesn't change its sign. It stays on the same side of the x-axis. But if the multiplicity is odd, the function crosses the x-axis, which means it changes the sign, right, if it crosses the x-axis. So this is the same thing. Look at my asymptotes. Each of those asymptotes had multiplicity of 1. I can kind of say that, right? It all had those factors to the power 1, and see what happens. At each asymptote, I have opposite signs, right? I have up and down and up, down and up, right? The sign changes at each asymptote. Do you see that? I also know that the multiplicity of that 0, that 2, was 1. So the graph will cross. It will not bounce off at that point. So we can use that. All right? And over here, the big thing was that there are no x-intercepts, so I knew it has to stay on the same time. Okay? So really, if I just erase all this, if I just erase all that, and if I had to do this problem all over again, because again, your book makes you do all that hard work, and then you pay the higher tuition rates, so then I can tell you the secrets. Right? Is that the idea? No? Okay. Because every time your horizontal asymptote is the x-axis, this is where it's hard. Because, you know, in the previous one it was easier because we knew we either stay above or below and just look at the x-intercepts. But here the x-axis is the asymptote. So all I need is just one point, okay? And usually 0 is the easiest point to plug in, but 0 is an asymptote, so I can touch that. So I'm going to take something really, really positive, 1004, doesn't matter. And I realize when I take a number that's really, really huge and I plug in for every x, I'll just get a positive result. So I know it's positive on this end. So bam, okay? Then I know this. The multiplicity of this asymptote is odd, so it has to change the sign. So it changes from positive to negative. Okay? It has to change the sign. Now I know multiplicity of 2 is also odd, so it has to change the sign there as well. So then it has to do that. It cannot bounce off, because that will imply even multiplicity. It cannot turn around and come back down. That will create another x-intercept. So the only option is to go up. Okay? Are you with me so far? Well, because there was just x minus 2 was a single factor. There are no powers there, right? Because that's where the 2 came from. 2 came from the numerator. So I'm just looking at the exponents. I'm looking at the exponents here, and they're all 1s. Yeah, they're all odd, so it will just be changing the sign at all of them. Okay? So therefore, it has to change the sign at 0, right? So it has to be below, right? But it cannot cross the x-axis because there are no more x-intercepts. So that means it has to turn around and go down again because there are no x-intercepts. It cannot go through because we didn't find any x-intercepts there. Are you with me on that? Well, I'm sorry. I have to keep repeating that. Well, then again, it has to change the sign. It was negative on this side, so it has to be positive on that side. So I'll get the same graph. Yeah? Let me try something like this. Don't write this down. I'll go very fast. I'll do the same one, but it's x minus 2 squared over x cubed, x minus 3 to the 4th, x plus 3, like that. Okay, I just threw a bunch of exponents all over that thing. It still has the x-intercept, x equals 2. The vertical asymptotes are still x equals 0, x equals 3, x equals negative 3. It's still that. And the horizontal asymptote is still y equals 0 because the degree of the denominator is 8 and degree of the numerator is 2. So it still has the same asymptotes and the same intercepts. So if I start sketching that, here is 2, here is 3, here is 0. I know it's weird. Here's negative 3, and here's 0 again. I know, I'll just use different powers. So we have that as an asymptote. Okay? So same starting point, only again, not drawn to scale. Negative 3 and positive 3 should be the same distance from the y-axis, right? Sorry about that. So again, I'm just going to grab a number that's all the way on the positive side, 100. All right? Because again, I just need a point to start. So if I take 100 and I plug in for every x, each of those factors will come out positive. Do you agree with that? 100 minus 2 is positive, 100 cubed is positive, 100 minus 3 is positive, 100 plus 3 is positive. Everything's positive, so it's positive. So it will do this. It will stay positive from that end. Okay? Now, x equals 3 is one of my asymptotes. Now, it came from this factor. That's where I got x equals 3 as a vertical asymptote. Now, what's the multiplicity? 4, right? That's even, means the sign will stay the same. It'll be on the same side of the x-axis, so that means it will stay positive there. And it will come down, it will hit the 2. Now, what's the multiplicity of 2? Even. So it still has to stay on the same side, so it will bounce off and will shoot up like that. And it comes to 0. Now, what's the multiplicity of 0? 3, so that's odd. So it has to change the sign. So it will start from the bottom, right? So you see, I went from positive to negative. Now, there are no x-intercepts here, so it has to remain entirely on the bottom. And then you approach the last asymptote, x equals negative 3, that has odd multiplicity, so it has to change the sign. So it jumps to the top. And that's it. So it's a different graph, right? We got a different looking graph. Here, all the signs alternated, right? Up, down, down, up, down, up. There we have few points where it didn't alternate. And you can, if you don't believe me, which you always should, we got time. That clock is fast, right? We got about 10 more minutes. I don't know why I'm talking so fast. Just test me. Pick any number on that interval, and see whether I'm correct as far as the location of the graph, except for something really positive. Well, I don't believe myself. I'm just making this up, maybe. Because it will be really beautiful how everything just tied together all of a sudden. Because that's what multiplicity was telling us with polynomials, whether it changes the sign or not. Right? Bouncing off means it stays on the same side of the x-axis, so sign stays the same. While crossing means it changes the sign. So that's really what we're studying here. Is it going to stay on the same side or change the sign? So, but anyways, if you just have one of those points, then you can start interpreting multiplicities for the rest of that graph. Isn't that fun? Does that make sense, what I was talking about? And again, if that doesn't make sense, you're more than welcome to pick a point from every interval, plug it in, and compute positive or negative. That just takes you extra, take us some extra time. I want to do one last example, and it'll take me really, it won't take long. Something like that. Okay? First of all, I would like you just kind of make a note how that is an even function, right? Just to test for odd even, so test for symmetry. That's always a good thing to do, because if you know the symmetry, all you need is a half of the graph. Then you either flip it around the origin or you flip it around the y-axis. And we do that by computing f of negative x, so it's 2 times negative x squared plus 1 over negative x squared. So all the negatives just go away. So that's 2x squared plus 1 over x squared, which is your original function, right? This is the same as f of x. So therefore, even symmetry around the y-axis. Okay? That will come in handy. Now, let's just verbalize this. Are there any x-intercepts? Remember how when we do the x-intercepts, so that's zeros of the numerator, and I should state that those are real zeros of the numerator. I don't care about the imaginary zeros of the numerator. I won't be able to graph them. But since the numerator is 2x squared, which is positive, right, plus 1, that's more positive, can the numerator ever be 0? 2x squared plus 1. So 2x squared plus 1, equals 0. So that means x squared equals negative 1/2. So no real solutions. So that means no x-intercepts. Right? The y-intercepts, if you put 0 for x, you'll get 0 in the denominator. Right? So no y-intercepts. So for the y-intercepts, you'll get 2 times 0 squared plus 1 over 0 squared, which is 1 over 0, undefined. So no y-intercepts, right? So no x-intercepts, no y-intercepts. Well, what is the vertical asymptote? What makes the denominator equal 0? 0. So x equals 0 is the vertical asymptote. What about horizontal asymptote? It's 2x squared over x squared. Well, it's the same degree. Yeah, it's 2 over 1, so it's just 2. Right? So if the degrees are the same, you just look at the coefficients in front. So it's 2 over 1. So since degrees are the same, we get y equals 2 over 1. So y equals 2. So that's all we have so far. We don't have any x-intercepts. We don't have any y-intercepts. We have a horizontal asymptote at 2. And we have a vertical asymptote at 0. Right now, there's only one way to sketch the graph of this function. There are no two options. Do you see that? What would you do on the left side of the y-axis? Go above, right? Why above? Because if you go below, you're going to hit the x-axis. There are no x-intercepts. So it has to be that, right? And the same on the other side, because it's now you can either say symmetries are on the y-axis, or you cannot go below because there are no x-intercepts. So the symmetry, you can really just say, well, now it's symmetric around the y-axis, so there's only one option. And that's it, we're done. So those asymptotes really guide us how the graph looks, what the graph looks like. Fun? I don't know what this says. 2 over 1, I assume. Oh boy, I don't know how you can read my handwriting. Okay, good. Well, good. That's not the end of 4.5, but it's close. Okay.